So I will briefly introduce myself. I'm a physicist by training here in France, as I said before, by theory. And so now I'm a freelance consultant. So my job is to introduce quantum computing to companies, so for them to start learning what's going on with quantum computing, what they can do with it, and what they will do in the next years. And in parallel, I have another job that is teaching quantum computing in engineering departments in different computer science schools and engineering schools here in France. So when we designed this webinar series with Tyrell, we had in mind an audience of non-specialists, so people like students, entrepreneurs, or executives. So don't expect a lot of heavy maths for this week, it won't be the case. So for today, we will dive into the world of quantum algorithms. So we will speak about potential applications of quantum computing in across sectors. We will review a bit what we mean by quantum speedup, what kind of acceleration we can expect. We will speak a bit about qubits and entanglements by trying to learn what's going on inside the black box. And we will finally review the quantum circuit model of quantum computation. So this is for today. On Wednesday, we will review quantum software platforms. So I will introduce more in-depth IBM Quantum Experience, which is a tool inside the cloud to access quantum computers from IBM. I'm not working for IBM, but this one is pretty easy to present. We will review Qiskit. Qiskit is a Python library for programming quantum algorithms and execute them on real hardware. And we will do a live coding session, so for you to have a chance to code your first quantum programs. And so finally, on Friday, we will speak more about the hardware, the limitation of current processors with noise. We will speak a bit about the quantum industry and about the financial initiatives, both private and public. So for today, we will remain with quantum algorithms. So before going more in depth with entanglement, qubits, and logic gates, and so on, I wanted to start this meetup with this molecule. This molecule is called the nitrogenase. This molecule is really helpful in the process of nitrogen fixation inside the vegetables. So it takes place inside an enzyme that transforms the N2 into NH3, ammonia, which is food for plants. This is a natural process. It takes place at about ambient temperature and ambient pressure. So I have a first question for you. You can start answering in the chat. I wanted to ask you how many classical bytes of memory we need to store in memory the whole electronic configuration of this molecule. I mean all the electronic structure, what we call the orbitals. How many classical bits of information do you think we need to store the whole electronic configuration of this molecule? Do you have any answer in the chat, Tyrell?
They're thinking.
They're thinking. What do you think, Tyrell?
One get from Amir. He's a regular. Hey, Amir. He'll take a guess at more than there are elements in the universe.
Yeah, something like this.
I think he knew. I think he knew.
I think you know. Yeah, you're right. Yeah, so I skipped this slide. I will go to the answer. So yes, it's something like about 10 to the power 32 bits of classical information to store the whole electronic configuration of this molecule. So now I have the same question for you guys, but about quantum. How many quantum bits do we need to store in memory, in quantum memory, quantum random access memory, the whole electronic configuration of the same molecule?
Bruno, should we call on someone?
Yeah, read the answers.
Amir.
I don't have any access to the chat at the moment, so you can read it for me.
Oh, that's right, you don't. Come on, somebody. I'm going to say, we're not getting any responses. Say the question again.
How many quantum bits of information, how many quantum bits do you need to store the whole electronic configuration of this molecule?
How many quantum bits do we need, folks? Iman out in Perth, 3 o'clock in the morning. He's saying 10 to the 16.
10 to the 16. It's much more or less.
I'm saying 100.
100, yeah, it's something like 100 because we have something
Yes.
like 100 of atoms inside this molecule.
New rule, if you get a correct answer, you get a free t-shirt.
So 10 to the power 32 on one side and 100 on the other side.
100.
So yeah, something like 100. I mean 100 of perfect qubits. I will explain more what I mean by perfect qubits on Friday. So 100 qubits in the quantum world, 10 to the power 32 in the classical. So because we need much more bits in the classical domain that we have with current and that we will never have with current classical computers, this problem is out of memory and it's not possible for us today to simulate this molecule. So for this reason, it's not possible to simulate the natural process of nitrogen fixation. So what people do in chemistry is that they are doing an artificial process for nitrogen fixation. It's called the Haber-Bosch process. It takes place at about 450 degrees Celsius and at about 200 atmospheres of pressure. So the energy consumption of it is about 2% of the world energy consumption. So it's really big. It's a really big amount of energy. It's about 2% of the world consumption. So you can start imagine the kind of problems that we can solve with quantum computing. We will review more of them in the next slides. So roughly speaking, when you are in the classical domain, if you want to double the classical power, you have basically to double the number of bits, of classical bits, so from n to 2n. In the quantum domain, if you want to double the computing power, you only need to add 1 quantum bit. It's not exactly about doubling the quantum power. It's more about doubling the memory space. We will be a bit more precise with this in the next slides. So what can we do with quantum computing? This is what I will present in the first section of the talk. So regarding applications of quantum computing, we can classify them in 3 main categories. So the first category is about predictions. So it's about machine learning, it's about deep learning, it's all about learning, let's say. The second kind of problem that you can solve is about optimization. So like the traveling salesman problem. So you want to go from point A to point B by passing through other locations. So what is the routes that will minimize the fuel consumptions, for instance? So this is really helpful for logistics and all these kind of things. And so finally, the last category of problems is about simulation, like the problem of the molecules, of simulating molecules for the pharmacology and the chemistry industry that I mentioned before. So I won't go in depth with math for all of them, but what I will do is that I will illustrate these 3 categories with domain-specific problems. So we will review different sectors of activities. And of course, we want everything to be secure. So I will also mention, I will also say a few words about cybersecurity, because quantum computing and cybersecurity are highly related. So the first domain I wanted to mention is chemistry and pharmacology. So at the core of chemistry and pharmacology, you will find molecules. Molecules are an arrangement of atoms, and atoms are quantum systems. So if you want to study molecules, you will need the Schrödinger equations, that is the equations that will describe the trajectory of quantum systems. But simulating the Schrödinger equations on the classical hardware is something that is really resource consuming. It's very complicated to simulate the Schrödinger equation on classical hardware. So what people in quantum chemistry are used to do is to make classical approximation of the Schrödinger equation. This is called, for instance, the Hartree-Fock approximation or the density functional theory. So this will work well with small molecules and with low excitation levels of electronic structures. So this approximation won't work for a big molecule and a high energy level within the electronic structure. So the biggest molecule that we can simulate at the moment is the caffeine molecule, which is a bit smaller than the molecules that we presented before. So with state-of-the-art classical resources, you are not able to simulate, for instance, DNA, which is a much more bigger molecule than what you can simulate at the moment. So with all this, with this, you will improve, for instance, drug discovery in pharmaceutical laboratory. You will improve catalyst study of catalyst process, like the one I mentioned before. You will also be able to improve processing of health data for bioinformatics and healthcare, and diagnostic for healthcare. So few months ago, the McKinsey and company wrote the following title: "The next big thing: quantum computing's potential impact on chemicals." So why such a title? Such titles coming from the fact that you don't need a lot of qubits to start simulating molecules for pharma and chemistry. With only hundreds or thousands of qubits, you can already start to solve interesting problems in chemistry and pharmacology. So probably chemistry and pharmacology will be the first industries impacted by quantum computing in the coming years. So a lot of effort is pushed in finding quantum algorithms to find interesting problems in these fields. So for instance, we can mention collaborations in between HQS Quantum Simulations, which is a German startup specialized in quantum algorithms, and Merck Laboratories that you probably all know. So Merck and HQS Quantum Simulations start working on finding algorithms for simulations of molecules in the pharmaceutical industry. So this is a first example. A second example that we can mention is the collaboration in between Atos and Bayer. Atos is a French company specialized in high-performance computing. So Atos is not really proposing a quantum processors like IBM or Google are doing, but Atos is proposing a classical hardware, a classical high-performance computing that can simulate the noise that you can find in quantum processors. So this way you can start handling quantum algorithms, small quantum algorithms, I mean, because you cannot simulate with classical hardware big algorithm. But you can start coding and you can start simulate small quantum algorithms and see what happens in the presence of noise during the computation. So Bayer and Atos are working together to find algorithms to process healthcare data to improve performance in the healthcare industry. Okay. So after chemistry and pharmacology, a second field that will be probably highly impacted by quantum computing is the field of the high tech. So of course we can mention machine learning and artificial intelligence. When we say machine learning, I mean it's all about training models, and training models is really resource consuming. So here, for instance, on the right side of my slide, you have an algorithm called AlexNet. AlexNet is a deep learning algorithm for computer vision. So this is the kind of algorithm that you will find in autonomous cars and all these kind of things. So as you can see, with a pretty good CPU with a 16 core, you need something like 40 days to train the model from scratch. It's a really long time. You don't want to wait 40 days to train the model. So instead of using CPU, what you can do today is to train the model with GPU. So here you have the Titan GPU. With Titan GPU, they're the best GPUs that you can find on the market at the moment. You can reduce the training process to something like 6 to 2 days. And 2 days, it's much better than 40 days, but it's still It's still not minutes or hours. So maybe with QPUs, we will be able to train a machine learning model in much less time than what you need now with state-of-the-art CPU and GPU. Another application will be search in databases. So I won't say much now on quantum search because I will detail the Gruber's algorithm that is a quantum algorithm for search in unstructured databases. But you can improve performance with search. And so until now, I presented quantum computing as an advantage, but quantum computing can also be a threat, especially in cybersecurity. I will say more on this in a few minutes. So if some of you are data scientists in the audience, you can find on the internet a quantum machine learning review on Nature written by Seth Lloyd and colleagues that present a large library of algorithms that will be useful to improve machine learning performance. So this is a really nice paper that you can find easily on Archive or Nature. Then I want to come back on the cybersecurity issue. So in cybersecurity, you have for instance, two people who want to share a message in a secret fashion. So a first way to proceed is to proceed with what we call the asymmetric key algorithm, like the RSA protocol that you can find on the internet with e-commerce. So for this, you have two keys, a private key and a public key. So for instance, I have the public key and the private key. I will communicate publicly, so I will communicate publicly the public key, of course, so everybody will get it. My colleague will use the public key to cipher the message with it. It will send me the ciphered message, so it's step 3. And because I have the public key, I can then decipher the message, the message. And the relation in between the private key and the public key usually is a relation of factorization. So to find the private key, you must be able to factorize the public key. This is the RSA protocol. And factorizing, if the key is long enough, is something that is really resource consuming. If you increase the size of the key, the time to solve the problem will explode. So with RSA protocol, I mean, it's very practical to implement. You communicate the public key and you decipher with the private key, but it's just a level of security that we call computational security. You don't know if there's an eavesdropper listening, but you bet on the fact that the problem that the eavesdropper has to solve is too complicated with state-of-the-art computational resources. So you don't know that there's an eavesdropper, but the problem is too hard for him to solve it. So you're secured. Now with quantum computing, we expect in maybe 10 years or 15 or 20 years, I don't know exactly, that we will be able to solve the problem of factorization with a quantum algorithm that is called the Shor's algorithm. I will say a word on it a bit later. So with the Shor's algorithm, you will be able to factor the large key, maybe in something like seconds or minutes. So the RSA protocol won't be secure anymore with the Shor's algorithm coming. We can also mention the Diffie-Hellman key exchange protocol or the elliptic curves cryptography. The Diffie-Hellman and the elliptic curves are some things that you can find in the blockchain protocols at the level of the digital signature, for instance. So RSA, Diffie-Hellman, elliptic curves are no longer secured with quantum computers. So a first thing that you can do to keep the information system secured is to switch from RSA, Diffie-Hellman, elliptic curves to other classical methods that are called lattice-based cryptography, code-based cryptography, or even multivariate cryptography. So we are, with those algorithms, we are still in the classical domain. There are still classical techniques, but we don't have yet quantum algorithms that solves these problems much faster than before. So it's still classical, but it remains secure at state-of-the-art quantum algorithm. So there's no quantum at this level, it's still a classical solution. This is what we call the post-quantum cryptography. So it's post-quantum, there's a word quantum, but there's no quantum in it. It's still classical security, but secure against the quantum computer at the moment. It doesn't mean that it will remain secure for years, but at the moment, we don't have quantum algorithms to solve these problems. So the National Institute of Standards and Technology is standardizing all these algorithms for industries, for companies to have libraries of algorithms to secure the data with them, in the next years. So this study is taking place at the moment, and we expect the results of this study for next year or maybe 2 years. So this is the first way to keep the data secure against quantum computers. Another way to do is to implement symmetric key algorithms. So with symmetric key algorithms, you have the same key for everybody, but this time the key is private. So we have the same key. The key is private. I cipher the message with the private key. I send the cipher message to my colleague, and because my colleague has the same private key, he can then decipher the message. So you have an illustration of it in the corner right. So you have a message M, a key K. You are adding the key and the message modulo 2, and then you apply again the key, and you come back with the initial message. So this is what we call the one-time pad encryption. So this time you have not. So this time it's information theoretic security. It's a much higher level that a much higher level of security than what we had before with computational security. Information theoretic security means that the security is guaranteed by the law of information theory. It's much more secure than what I mentioned before with asymmetric key algorithms like RSA. But this way to do is impractical because the two people need to share the same key before to use it. So if they want to share to have the same key, they have to share it. So they have to call each other with a phone call, or they have to share the key with an email. But an email or a phone call is not something that is very secure. So this method is not really practical, but the level of security is better. So now what you can do is to combine symmetric key algorithm, like one-time pad, with what we call quantum key distribution. Quantum key distribution is quantum. So the basic idea is to use quantum system like single photons that you will transmit in an optical fibers. And the basic idea is that you will encode 1 and 0 in degrees of freedom of photons, like for instance polarization. And because the quantum system is something that is very fragile, very sensitive, if an eavesdropper wants to get information on the key that is encoded on photons, it will disturb the state of the quantum systems. So you can see or not, you can see if there's or not an eavesdropper on the quantum channel when exchanging the key. So if there's an eavesdropper on the channel, then you won't use anymore the key. But if there's not an eavesdropper, then you can use the key by doing the one-time pad as I presented before. So you need a quantum channel to share the photons, and you need a classical channel for post-processing step to check if there's an eavesdropper or not listening on the quantum channel. So this is the basic principle of what we call the quantum key distribution. And after that, you can use the key to do the one-time pad as I presented before. And so everything is secured, guaranteed by the law of quantum physics and information theory. So it's both information theoretic security and it's practical because you have a secure channel to share the key offered by quantum mechanics. Okay. So a company selling quantum key distribution module is ID Quantic. ID Quantic is a Swiss company from Geneva. And they're working in close collaboration now with SK Telecom. SK Telecom is a telecom operator in South Korea. And ID Quantic and SK Telecom are working together to secure the new 5G network of SK Telecom in South Korea with QKD. So QKD is much more mature than quantum computing, as you can start implementing QKD in telecommunication infrastructures at the moment. Well, so chemistry, high-tech, cybersecurity, and no industrial goods. So as I mentioned before, quantum computing can be really helpful to improve to solve optimization problems that you will find, for instance, in logistics, like scheduling, planning, product distribution, routing, and everything. So this is the first use case. You can also improve, for instance, material science, like designing a more efficient battery. What else? You can also improve traffic simulation, which is a really heavy mathematical problem to solve. So this is the kind of things that you can do in industrial goods. For instance, Mercedes, the German company, start to collaborate with IBM to find to study catalytic chemical reaction in batteries in cars batteries to find better batteries. Volkswagen is collaborating with a Canadian company called D-Wave for traffic simulation optimization. Yeah, so that's another example. Another domain that we can mention is, of course, finance. In finance, there's always a trade-off in between the speed of investment, because you want to invest faster than another bank, but you also have to estimate the risk. So it's a trade-off in between the speed of investing and the speed of estimating a situation. So quantum computing will be helpful with that, with trading strategy, portfolio optimization, asset pricing, fraud detection, risk analysis, market simulation, and so on. For instance, Barclays, the bank Barclays, the Barclays Group, is collaborating with IBM to study the impact of quantum computing on finance by finding new algorithms to improve the process. A company also like JP Morgan is building up a team of quantum experts to study the same kind of problems. And so finally, a last domain that I wanted to mention is energy, like energy optimization with the smart grid. When you want to sell a mix of energy, like what you do with the smart grid, it's really complicated to match the production with the demand. It's very complicated math problem, graphs problems. So quantum computing will be helpful with that. And also another problem that we can mention is the processing of data that are coming from finding oil in the floor. So you process with seismic waves. A lot of data we came back from the floor, and so you can say if it's oil or anything else. But the amount of data to process is really big, so it's very complicated at the moment with state-of-the-art classical resources to process this data. But with quantum computing, we can expect to do better. So we can mention a collaboration in between ExxonMobil and IBM on this topic, as well as Atos with Total. And we can also maybe mention collaboration in between Microsoft and D-Wave. D-Wave is a Dubai company for for the smart grid optimization. So Microsoft and Dewey are collaborating on finding algorithms to improve the processing on the smart grid in Dubai. Do we have, Tyrell, maybe any question at the moment? Do we have some questions?
Nope.
No?
It's
Not
all
yet?
quiet.
Okay. So I said that we have...
And as some background, I'm sending them links to some of the articles and some of the pages you pull up.
Mhm. So far I said that we have many problems that are complicated, but I didn't really explain what complicated means. So this is what I will try to explain in the next section about quantum algorithms. So to illustrate this, I will first mention the integer factorization problem that I already mentioned with RSA. So with integer factorization, for instance, if I give you 15, it's pretty easy to tell me that 15 is 3 times 5. But if I give you a 617 digits key, which is a 2048 RSA key, in bits, it's much more complicated to tell me to find the prime factors of this sequence. So I have a new question for you guys. How many, I won't say seconds or minutes, but years, how many years do you think we need to find the prime factors of a 616 digits RSA key? How many years do we need to find the prime factors?
Iman suggests age of the universe.
Age of the universe.
Helen knows 1,000,000 years. So
Yeah,
there's two pretty close guesses.
It's much more than 1,000,000 years.
More than 1,000,000, Helen.
Yeah.
How about Iman's age of the universe? What do you think?
Age of the universe, it's something like, what is the age of the universe? I don't even know. Yeah.
Another one is, and probably this is the best way to think of it, mostly impossible with the current hardware, if not entirely impossible.
Yeah.
And then we got 13.4 billion years.
Yeah, this for sure it's impossible.
Lonal is saying 100 to the 100th.
Yeah,
I don't know what the units are though.
Yeah, it's something like 10 to the power 14 years.
10 to the power of 14. Okay.
Yeah, assuming a clock rate of a gigahertz clock rate. At gigahertz rate, we have something like this.
Well, let me read some more responses here because they're interesting. I think they're all vying for this T-shirt that doesn't exist. You got 13. Iman checked out. The universe is 13.8 billion years old. VG guessed 14 billion, and yeah, that's the age of the universe. So I think we concluded the age of the universe is around 13 to 14 billion years. I guess is that light years or just years?
Yeah.
But no problem. A quantum computer.
We won't solve it during the weekend. That's the message.
Yeah, that's the assignment. You need to know the exact answer by Friday's session, folks.
Yeah. And with a quantum computer, we'll only need something like 10 seconds, assuming a quantum computer with something like 4,000 perfectly stable qubits. I will explain more on perfectly stable qubits later, but with 4,000 logical qubits, we can do it at within 10 seconds, assuming a clock rate of something like megahertz. I don't think that the first quantum processors will be really fast, so we can assume something like megahertz. And with megahertz and 4,000 qubits, you can solve it in like 10 seconds. And if people are interested, I can send a paper on those numbers. Well, so in the quantum algorithms that allow us to do it that fast is the Shor's algorithm. I won't say a lot of Shor's algorithm, but the Shor's algorithm typically transforms a problem of factorization into a problem of period finding with a Fourier transform. And the Fourier transform provides an exponential speedup to find periods inside a signal. So this is the Shor's algorithm. It's an example of an exponential speedup. So to illustrate what is an exponential speedup, let's assume that you have the following keyboards. So with 10 digits and a passcode of 1 digit. So how many tries do you need to find the good answer? In the worst case scenario, it will be something like 10, in average 5. If you're really lucky, it will be 1. Now, if the passcode is about 4 digits, you will need 10 to the power 4. So 10,000 tries if you're unlucky. And if it's 6 digits, it's about 1 million tries. So as you can see, with the problem size, we have an exponential increase in the number of tries.
But you risk. So it's a trade-off in between the speed of investing and the speed of estimating a situation. So quantum computing will be helpful with that, with trading strategy, portfolio optimization, asset pricing for detection, risk analysis, market simulation, and so on.
Sorry, there's an echo. I can hear my voice from 1 minute before.
The Barclays group.
Yeah, it's better.
Mike, I had to mute you. You're not coming through coherently at all. Sorry.
It's okay. Thank you. Okay, so you can see there's an exponential increase in the number of tries versus the problem size. So this is typically the blue curves that you can see here. With a classical computer, sometimes, like the problem I mentioned before, there's an exponential increase in time to solve with the problem size. Now with the quantum computers, as you can see with the green curve, you will have a polynomial solution for the kind of problems that I mentioned before. So it's a big improvement. So this is typically the Shor's algorithm. So the Shor's algorithms fall into this category. But unfortunately, all the problem doesn't increase exponentially in the classical domain. For some problems, we have a polynomial solution. But even in this case, the quantum computer can improve the performance. If I zoom on this area of the curve, this is typically what you will get. So the blue curve is a classical computer and the green curve is a quantum one. So the gap in between the two curves is not as big as before, but it still remains interesting. And this is what we call a quadratic speedup. So to illustrate this second category of problems, let's bring back the mobile phone. So this time the passcode is 1 digit, but the side of the keyboard will change. So 1 digit, 1 number, so 1 try. 1 digit, 4 numbers, 4 tries. 1 digit, 6 numbers, 6 tries, and so on and so on. So the problem scale in a linear fashion. In computer science, you will find this kind of behavior when looking for searching, when searching in unsorted database. So let's take an example. So here's an unsorted database with number going from 1 to 100. It's unsorted. And let's say, for instance, that I'm looking for the number 70. So how many requests do I need to the database? So if I'm lucky, it will be 1. If I'm unlucky, it will be 100. And in average, it will be something like 50. So in the classical domain, if I'm worst case scenario will be 100. But in the quantum domain, it's only 8 tries. And more generally speaking, when you have n tries in the classical domain, it's about square root of n in the quantum domain. So it's not as interesting as before with the Shor's algorithm. We don't have 10 to the power 14 versus 10 seconds, but we have something like, for instance, 100 versus 8, which is still an improvement. And the improvement is more interesting as long as you increase the problem size, of course. So searching in an unsorted database, the corresponding quantum algorithm is what we call the Groover's search algorithm that has been developed in the 1996. The Shor's algorithm is from 1944. So it's they are quite old algorithm. So keep in mind this example because I will detail it later in the talk. So now we will try to understand a bit what's going on inside the black box. So I will now introduce the notion of quantum bits and entanglement. So to better understand what is a qubit, I first have to explain what is a state superposition, which is at the core of quantum processors. So to illustrate this concept, I will take a donut. So if the donut is on the right face, let's call it 0. If it's on the blue face, let's say it's 1. So with classical bits, you have either 1 or 0. But now in the quantum domain, you can have a mix of them. So it's like you have a single donut that you can observe with an angle. So for instance, by turning it off half, this is typically a perfect mixture. This is typically a superposition of red, a symmetric superposition of red and blue, 50-50. But what is complicated to understand is that the system, the donut, will remain in this superposition until you're not observing it. When you will observe it, it will fall on one of the two faces. So either red or blue. So for instance, you have 50% chance of turning on the red face when observing it. This is what we call a measurement, and 50% chance of obtaining the blue face when measuring. And this is totally random. This is what we can call a true random number generator. So it's not like one time we prepare it red, the second time we prepare it blue. It's really a superposition of the two colors inside the same system. It's not a stochastic distribution. It's really quantum superposition. We don't have the same in the classical domain.
Hey, Bruno?
Yeah.
Got a question in here. And so 100 is the worst case guesstimate. What's the statistical average in that? Do you know? How many steps?
How many steps do we need to find the distribution, you mean? How many okay.
Yeah.
Okay. I'm not sure to understand the question, but I will answer anyway. If you prepare one donut and you measure it, you will find either blue or red. So you don't know with only one measurement if the donuts were 50-50 or 70-30 or even 60-40 or anything else. So if you want to access the probability distribution, the ratio in between red and blue, you have to prepare a second donut and a third donut, and you have to measure all of them. So you will have at the end a statistical average. You will have let's say maybe 1,000 measurements, and from those 1,000 measurements, with a statistical average, you can say if it was 50-50 or 60-40 or 70-30 and so on.
Yeah, the questions always lag a little bit. This is going back to Grover's.
I will detail the Grover's algorithm later.
Oh, okay.
So we can keep the question for after.
I'll bring it up.
Yeah, perfect. So I will continue.
Yeah, I got a question here. Amir's asking, was there any specific reason or meaning behind using the donut in this case versus the more typical block sphere when we talk about things like superposition?
Yeah.
Is there some signal you're trying to send there?
Yeah, I didn't choose the block sphere representation, which is better actually, because I didn't want in this presentation to present the state vector formalism, to do math and all this kind of things. So I didn't want to introduce mathematics.
Oh, okay.
Presentation.
Yeah,
so,
donuts are much friendlier.
They are much friendlier, but not that much, because they don't really capture the complex nature of the coefficients in the superposition. So you cannot capture all the subtlety with donuts, but for today it's enough, I think.
Okay, just a question, that's all.
Yeah. But of course, the block sphere representation is much.
It's more intimidating.
Yeah.
I remember the first time I started digging into that, I was like, oh my gosh, what have I gotten into? Donuts, I can understand.
Yeah. So so this is what I said before. With if you prepare multiple qubits and that you measure them, you will have access to the coefficient, not the coefficient of the superposition, but you will have access of the probability distribution. So you'll be able to say it was 70-30 or 50-50 or anything else. So quantum mechanics is there is a statistical interpretation of quantum mechanics. It's not one shot. To interpret it, you need many shots. So let's go now on. Let's say words about the information inside the systems, the amount of information that is contained inside the quantum system. So when you generalize so for instance to two donuts. So in classical domain for 2 bits you have four configurations, so red blue, blue red, and blue blue. Now in the quantum domain, you can generalize the concept of superposition. So you can have 25% of red, 25% of red, blue, and so on. So in the classical domain, one bit is 1 bit of information. So with 2 bits, with 2 donuts, you have 2 bits of information. Now in the quantum domain, you can see the coefficients inside the superposition somehow as information, of bit of information. So with 2 qubits, you have 4 bits. You have the equivalent of 4 bits of classical information. With 3 bits of information, of classical information, you have 3 bits. With 3 qubits, you have the equivalent of 8 bits of information, 2 to the power 3. So now with n qubits, you have 2 to the power n bits of classical information. So now you understand better why we had 108 qubits in the quantum domain and 10 to the power 32 in the classical domain. Because 10 to the power 32 is about 2 to the power 108. Now a second concept in quantum information theory that is very important is the concept of entanglement. Entanglement is just a special case of superposition with multiple systems, with multiple qubits. So let's go back to the following examples. We have two donuts, 2 quantum donuts in a superposition of 25, 25, 25, 25. But now we can also do a superposition the following way. So we can suppose we have 50% on the red and 50% on the blue blue. When you will perform a measurement on the system, suppose that you obtain red for the first subsystem. So the first donut is measured in the red configuration. Then you don't need to measure the second donut because you already know the second donut will be also in the red configuration. So entanglement is all about correlation. When you measure the first one, you already know the results on the second one without measuring the second one. And same here, if you measure the second one in the blue configuration, you already know the first one is now in the blue configuration as well. So this is what we call entanglement. So this is perfectly correlated. You can also change to 70-30, it's still correlated, but more often you will get red instead of blue. You can also do anti-correlated entanglement. So blue, red, and red, blue. When you get blue, then the other one is red. When one is red, the other is blue. So it's still correlated, but anti-correlated. So this is entanglement. And entanglement, you will see in the third lecture, it's very helpful to perform error correction in processors. But I won't say more today. So with entanglement and qubits, you can start building algorithms with quantum circuits. So what can we do? As we said before, we can do superposition, we can do entanglement, we can do, for instance, a bit flip from red going to blue and the opposite, and we can also perform measurements. And so for all of this operation, in quantum computation, we have what we call quantum gates, quantum logic gates. Each of these operations is associated with one or many quantum gates. So for instance, if you want to perform a superposition, starting for instance from red, and you want to go in a 50-50 superposition, there's a gate called the H gate, Hadamard gate, the Hadamard gate takes a 0 and transform it into 0 plus 1. And the H gate also take 1 and transform 1 into 0 minus 1. So from classical bit, you go to a quantum bit, let's say. A second gate is the C0 gate, the control not gate, a control X gate. So the control X gate works the following way. You have a control bit, a control qubit, a control bit on the top, and a target bit on the bottom, a target qubit. So control and target. If the control bit is in state 0, then nothing happens on the target bit. But if the control bit is in state 1, then you will flip the target bit. So this is in the classical domain. But in the quantum domain, what you can do, so instead of starting with 0 or 1 for the control bit, you can take a control bit in a superposition of 0 and 1, like a 50-50 superposition. And by doing so, by linearity of the quantum theory, what will happen is that you will obtain an entangled state at the end. So Hadamard gate combined with a C0 gate, and then you result with entanglement. So the C0 gate is sometimes called the entangled gate, the entanglement gate, the entangled gate. So here, as you can see, you have 50-50 red-red and 50-50 blue-blue in the superposition, in a quantum superposition. Then the X gate allow you to perform a bit flip from red to blue, from blue to red. Also, something that I didn't say is that in quantum computing, all the operations have to be reversible. So if you can do it in one side, you can also do it in the other side. Everything has to be reversible in quantum computing, and except the measurements. And so the measurement, you will represent it with a little arrow like here. So we can build a first quantum circuit. So for instance, we can take a classical bit, put it in quantum superposition of 0 and 1, and then measure it. So this quantum circuit is what we call a quantum random number generator, because in 50 cases, in 50% cases, you will get blue, in 50% cases, you will get red. So if you reproduce this, you will generate a sequence of random numbers. So this is a perfect quantum random number generators with true randomness. Okay, a bit more interesting is the Grover search that I already mentioned. So we will detail it step by step. So suppose that you have an unsorted database of 4 entries. So 0, 1, 2, 3. And suppose that you are looking for the number 3. So I will try to convince you that in the classical domain, you will have to request the database 4 times in the worst case scenario, in average 2, but in the worst case 4. But in the quantum domain, you will need only one try, only one request to the database to find the good solution. So the first thing to do is to map the digital to binary. So we need for 4 entries, we need 2 bits of information, of course. And I remind you that we are looking for number 3, so 1, 1 in terms of bits. So because we need 2 bits, in the quantum circuit, you will have only 2 registers, 2 lines. So the first step of the algorithm, of the Grover search algorithm, is to put everything in superposition. So I remind you that superposition can be achieved with Hadamard gate, H gate. So we put an H gate on the 2 registers to put everything in superposition. So this is what happened. 25% of 0, 25% of 2, 25% of 3, and 25% of 1. So at this level, we cannot distinguish anything. Then the second step is what we call the oracle. So the oracle typically will tag the states that you are looking for. So here, for instance, this oracle is specially designed to tag the value 3. So it will change the sign inside the superposition of the terms that you are looking for. So everything is positive except the solutions that you're looking for that become negative. So instead of having 0, plus 1, plus 2, plus 3 in superposition, you will have 0, plus 1, plus 2, minus 3. So with the oracle, you can start differencing the solution of the problem from the other solutions. But if you measure directly now, what you will get is only noise. I mean, it will be 25% 0, 25% 2, 25% 3, 25% 1. The measurement is insensitive to the phase, to the local phase, I mean to the sign. Either if it's plus or minus, it doesn't make any difference for the measurement. So we must not directly measure at this step. Then third step is what we call the reflection step. I won't detail all the gates, but on the graph, what happened? The reflection step is like computing the average of the 4 coefficients in the superposition and flipping everything regarding the average. So we start from the white configuration and we end up with the blue configuration. So as you can see, the solution of the problem is now about 100%. And the 0, 2, and the 1 that are not solutions of the problem are about 0% in the superposition. And so finally, we just need to measure. And so in 100% cases, or almost 100%, we will get the good answer. So when I say that in the quantum domain, we need only one request to the database, what I mean is that we only need to do one time the step 2 and step 3. So you perform step 2 and step 3 only one time. Now let's imagine that you have a 100 size database as before. Instead of 4, you have 100 numbers now in the database. So instead of 2 registers, you will need 7 registers because 2 to the power 7 is about is 128. So you need you need 7 registers to encode 100 different values. And instead of performing step 2 and step 3 only one time, you will repeat the 2 steps, step 2 and step 3, 8 times, as I said before. And so the equivalent in the classical domain will be to perform step 2 and step 3, not 8, but 100 times. So this is what I mean when I say 100 versus 8 times in the quantum domain versus the classical domain. So it's about step 2 and step 3. So this is what we call step 2 and step 3. This is what we call the amplitude amplification step. So we have to repeat amplitude amplification step 8 times, or square root of n times, more generally speaking. Is it all right for you guys? Do you have any questions?
I'm not sure if this is in tune with what you had said earlier, because I go in and out a little bit. But it's a really good question. Did you mention that gates need to be reversible?
Yes.
Yeah, so do you have a good answer for that? Why these gates need to be reversible?
Yes, they have to be reversible because, okay, I will do math for a minute. In quantum information theory, I mean quantum mechanics, the vectors, the information is represented in what we call Hilbert space. Hilbert space. In these spaces, in these algebraic structures, I will switch to, I had a slide to answer this question. Wait, I will start to say that a classical bit is just 0 or 1. A stochastic vector, what we call a probabilistic bit, is a superposition of 0 and 1, but not like in the quantum domain. With a stochastic vector, the coefficients in the superposition that I call P0 and P1 are positive real numbers. And this is the main difference with the quantum domain. In the quantum domain, the coefficients in the superposition can be complex numbers. And because those numbers can be complex, the coefficients can be negative, which is not the case in the classical domain. In the classical domain, in a stochastic superposition with probabilistic bits, the coefficients have to be positive, which is a really big difference. And so because the numbers are complex, they can be negative. And so you can make interfere positive states, what I will call positive states, with negative states. With, I mean, superposition with positive sign and superposition with negative signs. And so by playing with quantum gates, by doing interference, what I call interference, you can reinforce the coefficient, which is the solution of the system, like we did with the reverse search algorithm just before. And so because the vectors are complex, the coefficients in the vectors are complex numbers, because we are working in what we call Hilbert spaces, the operation that you can, the evolution of the state, the operations that you are allowed to perform, they have to be unitary. In the classical domain with probabilistic bits, you are working with what we call stochastic matrices. That is matrices where the coefficients, the transition probability from one state to another, are real coefficients. And those real coefficients, when you sum the line, when you sum the coefficients in the same line of the matrix, it sums up to 1. In the quantum domain, it's not the same case. In the quantum domain, the operation has to be unitary. It means that the matrix representing the gate and what we call the complex conjugate operators, when you multiply them, when you multiply the gate with its Hermitian conjugate, then the product of these two matrices has to be the identity matrix. And because it's unitary, it's reversible. But the opposite is not true. It's not because it's reversible that it's necessarily unitary. So because it's unitary, because of the structure of the Hilbert spaces, you have to work with reversible operation in quantum computing. And I can say something else on this. Because it's reversible, there's no heat that is produced when you are performing a quantum computation. So, a perfect computation, I mean, without noise in the process. So quantum computation, it will be the first time in the history of computing that will increase the computing power without increasing the consumption of energy and without heating the environment. So I think this is something very interesting in terms of energy saving. Did I answer well?
That's probably the toughest question to answer. I heard one person say, why reversible gates? Because that's the way nature works.
Yeah, we can say.
In short.
It's reversible because the coefficients in the superposition can be complex. And because it's complex, then the operations that you can do on them have to be unitaries. And because it's unitary, it's reversible.
Okay.
Yeah.
Let me restate it. So because we're in a complex numbering system, I forgot the second step there. So the beta or the
do you want me to repeat?
Yeah, say it exactly what you said. I'm going to write it down because that sounded like.
Sorry, I said because we are working with complex vector spaces, because the coefficients can be complex, then the operations that you can perform on a qubit or a multi-qubit, doesn't matter, all the operations that you can do, all the gates that you can implement, they have to be unitary. Unitary means that the matrix multiplied by the Hermitian conjugate. Hermitian conjugate is just the complex transpose of the operator. So when you multiply U, I mean the gate, with U dagger, with the Hermitian conjugate, then the product of these two matrices has to be equal to the identity. And so because it's unitary, it's reversible. Unitary induced reversibility. But keep in mind that the opposite is not true. It's not because it's reversible that is also unitary. All right? I'm sorry, it's a bit mathematical answer, but I cannot answer better than this.
That's the best one I've heard so far in my career. It's a tough, it's a question I think a lot of us newbies, we struggle with.
Yeah, and this is what I said, that the donuts representation cannot capture this level of subtlety. Because when I presented the donuts, it was like presenting a probabilistic bit. When I explained, it was not very different that you can see in the middle of the tab of the slide. But quantum mechanics is much more subtle. It's not just a sum, a distribution. It's not a stochastic vector. It's not a probability distribution. It's what we call probability amplitude. Alpha 0 and alpha 1, they are not probabilities. They are not real coefficients. They are what we call probability amplitudes. And probability amplitudes are not probability. They can be complex number. And if you want to access probability, then what you have to do is to normalize the coefficients and take the square of it, like here. And after that, then you have a stochastic distribution. But at the heart of quantum computing, are complex numbers. And this is, yes, really complicated for, I would say, newbies for beginners to understand it. And because we have complex numbers, we can have positive and negative superposition, and you can make them interfere. And because they interfere, then there's an interesting speed up. It's because of complex numbers that there's a speed up. It's not because of superposition. There's a speed up because of superposition and interference. If you only have superposition, there's no speed up. You need superposition and interferences that are coming from complex numbers. So if you understood this, you already understand a lot.
At my end here, and hopefully others wrote it down to ponder later. You know, we just live in a Newtonian world, as they say. And if I take a bite out of the donut, there's no going back, right? So that's one of the hurdles I think we have, is we're not in a Newton world at the quantum level.
Yeah, and something that I can add to my answer is that, okay, it's forbidden to perform non-reversible operation, but if you're smart enough, you can transform a non-reversible operation into something that is reversible. And to do it, you will need auxiliary qubits. So you will perform the transformation with some registers in the circuit, and you will save the input state on an auxiliary register. So, like for instance, if you are computing the absolute value, if I tell you that the operation that you are performing is absolute value, and that I give you the result, you are not able from the output and from the operation to say if the input was positive or negative, right? So it's not reversible. Absolute value is not a reversible operation. But if you save in an auxiliary qubit the sign of the input state, if you can save in an auxiliary qubit if it was positive or negative, then at the end you have the sign of the input state, you have the operation, and you have the output. So you can do it in the reverse side. So it's reversible now. But you need an auxiliary qubit to make the absolute value computation reversible. So the price to pay, it's a resource.
But so the physics will stop us if, you know, let's say we did the absolute value and we put the sign in an auxiliary qubit.
Yes.
Okay. Now, what if the auxiliary qubit decoheres, disappears?
That I will answer on Friday.
Okay. There you go.
One pain per day. Good.
I got one comment here before I'll get out of your way. So Quan Ho said, qubit vector is defined in Hilbert space.
Yes.
Any gate is a quantum operator, which defined by a unitary matrix in Hilbert space. Okay. So I think what you said. I think he's repeating what you said. Unitary operator is reversible. The gate is a sequence of operators. Thus, the whole computation sequence would be reversible.
Yes. If all gates are reversible, then the whole sequence is reversible as well.
All right. Now I'm going to try to shorten that someday and make it small enough to put on a T-shirt, and then see what kind of reaction I get when I'm walking down the street. Thanks for the answers. The upper space correlated. Yep. Okay. All
Anything
yours.
else?
No. No.
No? Okay.
Thank
so
you.
We are done for today.
Oh.
So yeah, that was the end. It's already 1 hour and 15 minutes. So I think it's enough. And so the teaser is that on Wednesday we will speak about software and implementation. So we'll have a chance to implement, for instance, the Grover's algorithms that we presented, that I presented today. So I will introduce you IBM Quantum Experience cloud solutions. So we can access real quantum processors based on superconducting qubits that I will introduce on Friday. And so we will start coding in Python. So if you know how to code in Python, it's perfect. If you don't know, you will see it's pretty simple. So don't be afraid.
Do you expect that people might be able to follow along, or would that just slow things down for you, and maybe they could follow along watching a recording later on?
I think I will provide you the materials to follow the. I will send you a Jupyter notebook with all the code. So I will send you the code, and I will comment the code step by step.
Okay. Since Bruno is finished today, he ate all the donuts. Any other questions before we end? If so, just put your name in the chat, and I'll unmute you, or you can unmute yourself.
Yeah. So if you want to keep in touch, here you have my email address. If you want to contact me in private, and you can also easily find me on LinkedIn.
Oh, bingo.
Yeah, I publish a lot of news on quantum computing and related things on LinkedIn, so you can find me here.
Okay.
Feel free.
Thanks, Bruno. I'll probably send you a request in LinkedIn.
Yeah.
Bingo.
Yeah. Sorry for my bad pronunciation. I'm very sorry.
Yeah.
I know it's terrible, but I'm really sorry.
No apologies, man.
Yeah.
I mean, I would. Hilbert space, of course, is the obvious one, right? How can a French person say Hilbert space?
Hilbert space, yeah. I'm really sorry for that. I will do my best.
Dude, no,
next
dude.
time.
No worries about that.
Yeah, I think the slides are self-sufficient. So.
Oh, okay. We got one question here before you go. Could you mention the difference in sampling and Born rules, which is shown in the last slide?
Yes.
The Born rules, yeah.
Yes.
Born rule.
Yeah. Yeah. What I mean by sampling is just classical distribution. It's like generating random numbers, 0 or 1. But the Born rule is about transforming complex numbers into real numbers. So the Born rules is the Born rule give you the probability of getting 0 or 1. So when you perform many measurements, you will have access to the modulus square of the coefficient. You will not access directly the coefficient, but you will access the modulus square of the coefficient. And this is a real number. And so if you know that in 70% cases you have a 1 and in 30% cases you have a 0, then you can generate random numbers this way by splitting by 7 times on 10 generating a 1 and 3 times on 10 generating a 0. This is what I call sampling. So the Born rule gives you access to the distribution. So you are accessing the probability distribution. And once you have the probability distribution, when you know what is the probability distribution, then you can sample from it.
So if I may,
yeah.
So the Born rule, which is a squared plus b squared, equals 1.
Is like you don't know what is the quantum distribution that you have. until you measure it, you don't know what you have.
Yeah.
So you need to measure many times the quantum systems. You have to prepare many times the same systems, the same states, measure it, and you will access the modulus square of alpha and beta. And when you know the modulus square of alpha and beta, you know what is the probability distribution. And from that, then you can sample.
So one way to think about it is, I think you said we're transferring,
we
first of all,
P0 and P1, and from P0, P1, then you can generate random numbers.
But we're transferring from a complex number to a real number. That's one outcome of the Born rule. But the other, to use a term you used earlier, which was new to me, we're translating, if you will, from a probability amplitude to a more like a location probability.
Yeah.
Would that be fair to say? Because
I missed a part of the explanation, but I think it was right. Yeah.
Okay. All right.
Sorry.
I can be dangerous when I don't know what I'm talking about. Anyway, a few comments here from people before we just shut off. It says, great presentation. Thank you. Thank you, Bruno. So knowledgeable. Thank you very much for a very good introduction. And if I can say on behalf of everybody, merci beaucoup.
Merci beaucoup, monsieur.
Monsieur. I forgot the monsieur part.
Monsieur.
Thank you. And most importantly, we'll see everybody, hopefully, and friends at the same time, same time on Wednesday, whatever time zone you're in. And if Iman shows up again at 3 a.m., I'm going to invent a T-shirt to send to him. But we'll see you again on Wednesday, and also don't forget to put in your calendars on Friday.
Yeah,
and
maybe on Friday I will ask you to change a bit the time zone. Maybe instead of 9 we will start at 6 in France, if possible. Well, I will send you.
We'll work that out.
Stay
tuned. Okay, stay tuned, people, and I will be sending out a new Zoom link for Wednesday. So we'll see you then. Thanks again, Bruno. Merci, and
thank you everybody for attending.
Bonsoir.
Bonsoir. Was my pleasure. So see you on Wednesday, guys.
All right. Bye.
Goodbye.